Hi everyone, welcome to today's webinar, Connexity Digital Twin of a Nuclear Plant Component. So we are joined today by some partners of the Connexity project. So Luca Bussina, Senior Product Specialist at ANSYS, Frédéric Praca, Software Architect at Assystem, Michael Lelimouzen, Data Scientist at Atos, Jaïv Roger, Research Engineer at EDF, and Richard Drews, Senior Sales Manager at Siemens. In today's agenda, we will cover the ongoing initiative, part of the Connexity project, Digital Twin of a Nuclear Plant Component. So we will start with an overview of the Connexity project with Jean-Yves, and then moving into the main feature of the ongoing initiative presented by EDF and Siemens Energy. ANSYS, Atos, and Assystem will present you the key components of the digital twin, illustrated by a live demo with Atos. And we will close the presentation with the key takeaways of the project before answering your question. So at this time, I will turn the event over to our first expert, EDF. Please go ahead, Jean-Yves.
Thank you, Graziella. First of all, let me first introduce you what is Connexity project in which the digital twin have been developed. Connexity is a EDF initiative regrouping 14 different partners from the nuclear sector, but also from EDF providers or any firms interested in the project. This project is connected to several other French organizations, as given in the right-hand side of the slide, if you know them. So in the next slide, we can see that the main goal of the project is to create new uses and services based on digital technologies to support the digital transformation of the nuclear industry. And all the developed products must help to reach this target. On the next slide, we give you the key feature of the project. As I said, there are 14 different partners and 45 contributors in the project. There is a physical showroom, the Connex Lab, based in EDF Lab Paris-Saclay, near Paris, where former developments and new ones are exposed. The project has a 2 years life cycle, allowing fast developments and evaluations of its operation. The final products might be considered as prototypes. This year, we are starting the third season of the project, and we are presenting you the result of the second season obtained on the digital twin part. For the third season, the objects developed in Connexity are the full-scale digital twin, which we are going to talk about after, Asways app to guide workers on the reactor building, the digital workshop, which correspond to the digitization of documents associated to nuclear workshop activities, and a new building information modeling approach for the building process of power plants. In addition, we have more developed products which are now developed in-house, but let me introduce you the digital twin that we have built all together. First of all, let me start with our own definition of a digital twin. The digital twin is a physical model connected to actual sensor data in real time. We are dealing with a part of an equipment or system for a specific purpose. We are not twinning the whole equipment or system for any purpose. And we are not manufacturers, and we are working with an industrial asset as design. As you can see in the Gartner figure, on the left side, there is a high level of expectancy in the digital twin technology, and we think it's worth it. In addition, as you can see in the right-hand side figure, we have a lot of enabling technologies which seem to be mature as HPC, reduction order model, AI, data assimilation, and so on. So we think that the technology is now available. So now let's start with the digital twin context. In EDF, we have a large digital system containing more than 20 years of operation for 44 54 power plants, even though we still need physical-based modeling and not only data-based model. For this specific use case, a part of the digital information is stored in various digital bases. They come from operating system, round systems, and concern thermal, chemical, and electrical data. In the Connexity project, we choose to address the generator as a proof of concept. And for this purpose, we are dealing with a system called NAFEA, which allows us to have access to the value of the magnetic field in the air gap between the stator and the rotor of the machine. As a first step, we work with a mock-up based in Saclay. On this machine, we already have a finite elements model and plenty of sensors. And we are able to simulate faults on the rotor winding. This machine was a good candidate to create a proof of concept of a digital twin. But now I let Richard from Siemens Energy present you the main feature of our digital twin.
Thank you, Jean-Yves. The generator digital twin is built on 4 major functionalities. Monitor, to visualize specific values and health indicators, as identifying deviation between the output from the reduced order model and the real measured values. Identify, to identify the most probable root cause for the detected drift. Confirm, to allow the operator to verify that the default is real and is in adequation with the digital twin results. Advise, deliver maintenance advices to the operator linked to the detected deviations. This functionality is also available when the machine is in a healthy state. All these functionalities are developed according to the respective competency from each Connexity partner. Reduce order model technology with ANSYS, data science with Atos and Assystem, IT integration with Atos, electromagnetic model turbo generator mockup as a fleet in operation experience with EDF, predictive and maintenance expertise with Siemens Energy. On the next slide, let's see the functional scheme. The generator digital twin was developed in 2 stages. An initial learning sequence starting from the real generator, its geometry, as well as data issued for measurements to generate a recalibrated electromagnetic model. Different simulation configuration was processed to generate specific data sets with and without defaults. Based on this, ANSYS was able to generate different reduced order models in healthy state as with defaults. This simulation data set was also utilized by Atos and Assystem to generate the fault classifier to identify the respective corresponding defaults. In the operation stage, here we use the functionality monitor to compare the measurements issued from the equipment with the results provided by the ROM in healthy state. If a drift is detected, the fault classifier model is engaged to identify the type of default encountered. Then we can engage the confirm step where a comparison is performed using a ROM with default to generate the confirmation. This allows the operator to verify that the default is real and not a false alarm. When the default is confirmed by the operator, the advice module will support him with specific recommendations. The whole operation process is interactive and is integrated within a HMI developed by Atos. Now, I'd suggest to look more specifically to some key components, and for this, I'll hand over to you, Luca.
Thank you, Richard. So the features that you've described relied on 4 key components that we will detail now. So our digital twin is a physics-based digital twin in the sense that its model rely on physics equation. So we are using a finite element solver to solve the electromagnetic equation that is called Code-Carmel. In this finite element software, we are building a model that takes as inputs the loading point, that is that are the reactive and the active power as well as the tension. As we give that as an input of the model, then we run the finite element solver, which perform a transient analysis, so that we get as a result the prediction of the electromagnetic behavior everywhere in the alternator, and we are focusing ourselves on the air gap between the rotor and the stator, where we are looking at the prediction of the tension in this area that we called virtual flux sensor. We are also using a map of the electromagnetic field to provide insight to the operator. The main advantage of this type of model is that we can benefit from the accuracy of the physical prediction. Another advantage is that we are able to model the asset with default, and this is another input of our model. We can choose if the model is simulate the asset in a LC setup or in a setup with some default. The main drawback of using a finite element software in the context of building a digital twin is that it requires too many computational resources to be able to run on an edge device and give prediction in a reasonable time. That is where the second key technology enter into the game, and this is the model reduction. The model reduction is based on a machine learning workflow where we are using the finite element software to generate some training data that span the behavior of the asset that is expected to run in. And then when we have this training data for both the asset with or without default, then we are extracting from the simulation data the reduced order model, extracting the physics from this result data, and then we are repackaging this ROM as a standalone digital object that we are then able to plug and play in the digital twin, and this provides at the end of the day the accuracy of the 3D physics with prediction that can be made in real time. Our model reduction is called non-intrusive. That is to say, we can use it with any mesh-based solver. We can extend our approach easily, thanks to that, to other type of physics, like thermal behavior or structural behavior of the asset. We are able to predict a linear or non-linear model, static or dynamic model, and in the context of connexity, model which represent LC behavior or behavior with default. For the connexity project, we have used more particularly a state-of-the-art response surface technology to predict the harmonics of the virtual flux sensor. We have also used methods based on projection onto reduced bases to predict the magnetic field inside the alternator, and made use of error predictor to assess the accuracy of the reduced order model. Once we have the reduced order model in operation, we can compare the prediction of the reduced order model with the measurement of the actual sensor data that come from the sensors, and then assess evaluate a drift, so that we are able to detect if the asset encounter an issue or not. And once we have detected that, we are predicting the type of defect that is happening, and this is based on classifiers that Frederic will introduce to you now.
Okay, thank you, Luca. So for the classifier, we are using the harmonics. So we get the temporal signal from the magnetical force, and we extract through to the frequency domain using a fast Fourier transform. Using this, we get all the harmonics, and we can then extract the relevant harmonics to feed the SVM, which is the support vector machine. So the support vector machine is a way to project the measurement inside a multidimensional vector space, and then we will use it to detect the defect. So during the first part, which is the training part, we use the data coming from Code Caramel, extract the relevant harmonics, and then project on the support vector machine. The goal of this is that we have the data that we know which state they are in. So we are able to label each data in the vector space. Using this, we can then use the SVM to calculate an hyperplane partitioning each defect types inside the support vector machine. During the inference, we use the data coming from the mockup, from the machine mockup, and then we extract the same way from temporal space to frequency domain, extract the harmonics by this mean, and then perform the recalibration to get the relevant harmonics. Once this is done, we can present the harmonics to the SVM, and the SVM will be able to determine which part of space the data will go on. And then, using this, we can exactly know which is the defect the measure is corresponding to. So SVM classifiers can predict likely alternator state and defect types. So we had two SVM, one for telling us if the alternator was healthy or not, and the second one which was determining if there is a defect and which defect it is. SVM are used to be modelized, optimized with large training data sets. So that's what we get through the Code Caramel. And each result is given using a prediction confidence. So we can have several defects and one which is a major one. So everything we've done inside the project was inside an IT infrastructure provided by Atos, and I will let Michael present it to you.
Thank you, Frederic. So each of the key components presented now have been developed as a microservice. The development of microservices facilitated IT integration in the project with the components coming from the different partners within the consortium. This was a suitable approach for such a collaboration. It enabled us to build a microservices architecture on the Codex Smart Edge platform. This IoT platform follows a DevOps methodology to get faster upgrades of the application and deployments. Open source technologies for containerization are used, such as Docker, Kubernetes, as well as standard messaging protocols, MQTT, for instance. Codex Smart Edge is a hardware agnostic platform. Within the Connexity project, we deploy our digital twin solution on various types of servers, either remotely or on the edge, so close to the asset. And now we're going to make a live demo to show the digital twin usage. So now I'm a user of a digital twin, and I have a secure access to the human-machine interface. In the homepage, the French nuclear fleet is displayed on a map. I can zoom in, and I select a site with monitored equipment, and I reach the monitoring dashboards. For the turbo generator of the Connex lab, the EDF lab in Saclay, we have a traffic light that indicates the general status of the asset. Currently, the light is green, so the machine behaves as expected. As a user, I access to technical documentation from where I can view the current operation conditions. As a technical expert or asset operator, the digital twin gives me monitoring, diagnosis, and recommendation tools that help me taking the right decision at the right time. The recommendations are available at any time, and they depend on the current state of the machine. Over time, the digital twin follows a decision tree that provide me the best advice in analyzing the evolution of the machine's behavior. As soon as a drift is detected, the traffic light turns orange. However, if a drift is only temporary, the system can recognize it and consider it as a false alarm and switch the light back to green. To compute the drift, the current measurements are compared to properties of the LC machine calculated by simulation using a reduced order model around. The drift is characterized through electrical frequency harmonics. For 9 characteristics harmonics, the deviation between measurements and LFROM can be monitored over time, and the score of instantaneous drift corresponds to the number of harmonics exceeding the respective deviation threshold. We can view on the score graph here in white the instantaneous score. The digital twin also calculates a cumulative score, which is the aggregation of the instantaneous score over time. We can see this cumulative score increasing here in blue on the graph, and here also in the gauche. There is also set here in red a threshold, a limit threshold for the values of the cumulative score. For more advanced analysis, the digital twin computes a magnetic field in the turbo generator. We can see a projection here through this cross section, and if we click on a quarter of a slice of this map, we view here electromotive forces at different positions of virtual sensor in the air gap. Also, we can view here a projection of recent measurements along the active power and reactive power of the turbo generator. And as an expert, I can identify a critical operating point where the highest score of drift are observed. The cumulative score has just exceeded the threshold limit, and the traffic light turned red. So the fault identification process has been launched, analyzing the points from the critical operating point detected. The first classifier estimates with certainty that the drift is due to a short circuit. The second classifier identifies the short circuit on the coils A1, B2, and B4, also with a high level of confidence. On the rotor map, we can see in red the slots A1, B2, and B4 where coils are suspected to be damaged. Again, we see a projection of the magnetic field along this cross section, but now for the identified short circuit. As for the LC state, we can view the electromotive force at different positions of virtual sensor. Thus, we can compare the theoretical signal of the identified short circuit with those from the LC state. The diagnosis of the digital twin is summarized here in this dashboard. I can use the recommendation menu that suggests me verification to do on the machine to assess or not the identified fault. Now, I consider that it's a real default identify, and I confirm it here. The recommendations are now to a level of confirmed fault. And I have at my disposal a flow chart with actions, evaluation, and possibly alerts to the teams to raise. In conclusion, to sum up, this demonstrator of the turbo generator demonstrates a generic approach enabling the implementation of digital twin solutions. This year, we will scale up to build digital twin of turbo generators of French nuclear fleet. We also look for other use case as the platform can host multiple sites and multiple assets. Now I give the floor back to Jean-Yves for the key takeaways.
Thank you, Michael. So let me give you some key takeaway. First of all, if you want to know the status of an equipment in real time, the digital twin will allow you to do so and more. First, you can monitor your asset and detect the drift of sensors. Then you can identify the root cause of the drift and the most probable fault associated. Therefore, you can confirm the defaults and share information accessible from the operators to the experts. And at any time, you have advices about what to do and check whatever is the machine status. So to sum up, digital twins need a wide range of knowledge, and we have been able to demonstrate that with several partners, technologies, integrated in an IoT platform, we have been able to monitor an equipment to detect and characterize the default and to allow visualization and interaction with operators and experts. Thank you very much for listening, and I let Graziella finish this presentation.
So thank you very much for this great presentation. As you can see on the screen, you can follow our Connexity partners on LinkedIn or check directly their website for more details on their activities. So I would like to thank you, Lucas, Michael, Frédéric, Jean-Yves, and Richard for your really great presentation today and your time, especially for this webinar. Ladies and gentlemen, this concludes today's webinar. On behalf of ANSYS and the Connexity partner, I would like to thank you for your attendance today. Thank you. Bye.